Hello and welcome back to Introduction to General Relativity. In lecture 4, today's lecture, we are going to look at the definition of tangent space for a manifold. If you recall, in the previous video, we introduced the notion of a smooth manifold, and also we commenced the definition of what it means to have a tangent vector to a smooth manifold. And the substance of that definition was that we were going to replace the ordinary geometric notion of a tangent vector to a smooth embedded manifold with the notion of a directional derivative. So today we're going to take a little bit more time investigating directional derivatives, their relationship to tangent vectors, and using directional derivatives as a means to define tangent vectors intrinsically. Hence, the first topic that we will cover today is that of directional derivatives as vectors. So this is maybe not the way you have been thinking about directional derivatives up to now, but you can think of directional derivative operators as vectors. I'll show you how you do it. You start with a n tuple of numbers from Rn, in other words, a vector, components of a vector. And you note that this defines a directional derivative. According or via the following formula. Directional derivative at a point as follows. The way this works is you suppose f is a at least one-time differentiable function, from Rn to R, and define v dot grad here. I'm using the Einstein summation notation to sum over this repeated index here, so I'll replace that with a summation today, but I probably in future will not do this. So v dot grad is a differential operator that you can define, but that's, and indeed that's a directional derivative, but I want to talk about the more specific notion of a directional derivative at a point. So I'll put this in brackets. So that notation means is this linear differential operator. But the notion of a directional derivative at a point, well, that's this notion here. You differentiate with respect to v dot grad the function f, and then you substitute in f as a function of the argument, and then you substitute in x is this point P that you care about. Although we write that this way. So this more specific notion only makes sense at a point P. That's what I mean by a directional derivative at a point P. So given a vector in Rn, we can define a directional derivative at point P by the formula in the red box here. Directional derivative at point P. Conversely, given a directional derivative at point P, we can obtain a vector. Given some v dot grad at some point P, I'll just use the point, the P, subscript P notation to indicate that you have to evaluate this at point P. We obtain a vector in Rn. Just read off those coefficients in the definition of a directional derivative at point P, and then you have yourself a vector in Rn. And further, and this is what encourages us to make this analogy between directional derivatives and tangent vectors concrete. Directional derivatives at P form a vector space. That we can identify with tangent space to the surface. And this is going to be the idea of directional derivatives at a point P. You know, here's the picture that we currently have. We have Rn here, we have a point P, and then we have this idea of a directional derivative at point P, and we're identifying that one-to-one with, here's the point P, and here's a vector V at point P that we think of as a tangent vector. So this correspondence between directional derivatives at P and tangent vectors, that's the way we're going to make sense of tangent vectors intrinsically for manifolds, because it turns out, although we can't define tangent vector directly intrinsically on a manifold, we can define directional derivatives at a point P on a manifold without making reference to the ambient space at all. Before we do that, we have to say what is it intrinsically that we want from a directional derivative at a point P on a manifold. And for that, I'm going to note two properties, right? Note v dot grad at P satisfies the following two properties. And these are crucial for our subsequent generalization of the words directional derivative to manifolds. Firstly, if you take the scalar combination of two functions, then the directional derivative at point P of these two functions is the scalar combination of their directional derivatives. So they obey a linearity. So for all fg functions and for all a, b real numbers, we have this linearity. And the second thing is the so-called Leibniz property. If you have two scalar functions f and g, you apply a directional derivative to them, then that's the same as evaluating the function at the point P and taking the directional derivative of the scalar function g, plus evaluating the function g at the point P and taking the directional derivative of P of f. That's the Leibniz property. And now some notation before we continue. In the previous video, in the additional material at the end, I referred to calligraphic f as a differentiable structure. Here, however, probably for the rest of this course, I'm going to also use calligraphic f of m as to denote the set of all C infinity functions from M to R, where M is a manifold. We will, this notion, it should be clear from the context whenever what I mean by the respective notations. And so the big idea now, to be able to define a tangent vector for a manifold, is to first define the vector space of directional derivatives on a manifold, and then just call that by fiat, just declare that to be the tangent space. And how do we define a directional derivative on a manifold? Well, we just take these two properties that are highlighted above, 1 and 2, and declare such maps to be directional derivatives. So we define a vector space Vp associated to a point P in a manifold M to be the set of all maps which goes from the space of C infinity functions on M to R which obey these two properties, 1 and 2. There's a little exercise to get you used to these kinds of things, and the exercise is to prove or to convince yourself that if h, so this exercise has a couple of parts. A, convince yourself if h is constant, then VH is 0. And you're only allowed to use properties 1 and 2. And the second part of this exercise is to convince yourself that VP so defined is a vector space. So you can add, subtract, blah, 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 multiply by scalars. So that's some exercises to get you warmed up into and used to this notion. Now we have to ask ourselves a question. It's all very well to introduce these directional derivative thingies that, do we dare call them directional derivatives on a smooth manifold? Well, not quite yet, because the question is, maybe we have created a monster. So what could have gone wrong? Well, in defining these linear maps, VP, these directional derivatives, V, satisfying those properties 1 and 2, it could be that we've created, certainly we've created a vector space. You've proved that to yourself in the exercise just then. But it could be that we've created a horrible vector space, a nightmare vector space with a continuous, with an infinite number of dimensions that has nothing to do with tangent vectors altogether. So e.g., we could have, even though we want to have a tangent space of dimension n, we may have inadvertently, by being careless in our definition, created a huge vector space, say an infinite dimensional vector space, which has nothing to do with tangent vectors when you specialize the notion back to Euclidean space. This is not the case. Obviously, I wouldn't have done that to it would just be a waste of your time. And there's a theorem that establishes this, firstly, that the dimension of this vector space is the hoped for n, and secondly, cements the notion of these directional derivatives as the correct analog of tangent vector. And that's the theorem we prove, or state and prove this theorem. Typically in this course I won't be proving theorems, but this one is a theorem that we can prove without too much difficulty and makes reference essentially only to multivariable calculus. And I think in going through the proof you gain a lot of intuition about this vector space. So we're going to go through the proof. However, for examination purposes I wouldn't really ask you to reproduce this proof. Here we go. So let M be an n-dimensional smooth manifold. I'm almost certainly going to drop real, smooth, these adjectives as we go along. We know what we mean in this course. We're going to be talking about real smooth manifolds. Let P be a point in the manifold, and let V of P be this thing we defined above, and we now call it tangent space at P. The theorem that we will, this theorem says that the dimension of V of P is exactly n. Okay, so that largely cements this vector space as a reasonable analog for tangent vectors, but as we go through the proof you'll see that it actually makes that connection slightly more precise. Before we do the proof, actually, I I'll just introduce some notation. Notation definition, I guess. And the reason we're going to introduce the notation is we're going to introduce a candidate basis for this vector space. And for that candidate basis, we need some notation, and it'll turn out that in fact, this candidate basis will be a very familiar set of things indeed. So here's my cartoon of a manifold M. We're going to consider a point P. We're going to consider the chart around the point P. We're going to consider the corresponding map to Rn, which we'll call psi. Consider the set in Rn that it gets mapped to, the chart, call it U, and the point P gets mapped to psi of P. We're also going to consider, also playing a role in this theorem is a function on the manifold F. The function maps just to the real number line, which is also a manifold. And there's the function evaluated at P. It finds itself on the real number line. And with this notation in hand, we're going to introduce a special basis now for tangent space. And let's see, let's declare what these objects are first of all before we move on. Let psi be a map from O, a subset of our manifold, onto Rn, 1-to-1, onto, be a chart with the point that we care about actually in it. No point choosing a chart where the point's not in it. Now, if f is a nice smooth function on M, then the first thing we can say is that the function f composed with psi inverse, right? You go back from Rn into the manifold, it maps from U inside Rn to R. Well, that's a C infinity function, right? If you just look at this diagram that I've drawn here, if I go backwards, I'm at psi of P inside Rn. Oops, I can see a mistake there. Rn. So if we're at the point psi of P and we go backwards via psi inverse, then we go down here via f, then what we've defined is a function that goes from U to R. And then what we're going to do is now, given, we're going to define for each of mu equals 1 all the way up to n, we're going to define the following operators. X mu, these operators eat scalar functions and produce numbers. And the scalar function that it eats is f composed with psi inverse, and then we evaluate it at psi of P. And these x mu's, these are the coordinates, our current coordinate system of Rn. Here's a little exercise for you before we get to the proof of the theorem. X mu so defined are tangent vectors. They're elements of this space Vp. It's very important that you go through that proof. Just have to check properties 1 and 2, linearity and the Leibniz property. Now let's get to the proof. So we've got this candidate basis in hand, and we're going to now prove that every element of Vp is a linear combination of these and vice versa. Now here we go. Suppose that big F now is some nice smooth function. Then there's a way to expand f looks like a Taylor series. It's really an instance of this intermediate value theorem. And here's the expansion in question. So it's possible you have a smooth function on Rn, right? Now, when you evaluate the smooth function at a point other than some given point A, then, well, you know, it's probably takes some other value. But if you were to, say, use Taylor's theorem, you might say that for x nearby to A, f is a linear combination of the coordinate differences. Okay, that would be Taylor's theorem. Taylor's theorem to first order plus some higher order corrections. But this theorem here, this result here, says something a bit stronger. It says that for any smooth function on Rn, it's possible to write that function at an arbitrary point x as the function evaluated at a fixed point A plus some coordinate differences times by, instead of the derivatives of our function, you know, the first order term in Taylor's theorem, some arbitrary infinity functions h mu of x. So this is, well, you know, mediumly irritating. It's not completely obvious how to prove this. So this is a bonus problem for you to prove this statement. There's a variety of ways to prove it. I know of at least two. You could do it by induction on the dimension, or you could use the intermediate value theorem, or the mean value theorem. I believe it's the mean value theorem, but I'm not, have to look at the proof again. Now these functions, these scalar functions h mu a, they have an explicit representation. They really are the first derivatives of f at x, as they should be when x is a, but when evaluated at a, but when h mu is evaluated elsewhere, then it's just some smooth function. Okay, so this little lemma is something that we're going to use in our proof of the theorem. And we're going to apply it precisely to the following scalar function. So we've got a candidate scalar function that we care about. We're going to say that big F is really F composed with psi inverse. And A is none other than the point that we get upon projecting P into Rn. So then, by star, so this result star that you've proved now in your bonus exercises, we have for all Q in our chart the following result. We have that f of Q is little f of P plus the sum x mu composed with psi evaluated at Q minus x mu composed with psi evaluated at P h mu psi Q. So I haven't done anything except take the definition. I've taken this particular choice of big F and this particular choice of A and substituted it in to this equation star, which is this result from multivariable calculus. That's all I've done. And when you do that, then you end up writing down the things that I've written down in star star. So now let's suppose that V is an element of this vector space that we created above. So it's a directional derivative obeying conditions 1 and 2. We're going to apply this operator to this scalar function f, and we're going to use this representation star star. So let's go through it line by line, see what happens. So we apply V to f, then according to star star, we'll just replace the argument f with this representation above. So I'm literally substituting star star in here in the argument. Dot, 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 dot. I'll just leave that stuff in the brackets for the moment. So I've taken this stuff, this representation here, and just pushed it into the argument of V there. Now let's exploit properties 1 and 2 of the operator V and on the argument and see what comes out. So we use linearity in the first and Leibniz property. So 1 and 2, I'm going to use them all at once. And if you use linearity, then this, when applied to this argument here, then you get V of f of p, which has to be 0, because f of p is a constant, and V of a constant is 0. You've proved that already. Plus, and then we use linearity to put it over the summation sign here, and the Leibniz property. And the Leibniz property says we must evaluate, when we have a product of two functions, we have to evaluate one at the point P and then apply V to the other. And that's exactly what we're going to do here. Setting Q equals to P or X equals to A. And then we apply V to the scalar functions H mu. But then the other part of Leibniz comes along and says, now we have to evaluate the H mu scalar function at P and then apply V to that coordinate stuff. And here I will start using the Einstein summation notation a bit more frequently to avoid writing out these summations all the time. Now, evaluating this term in yellow here at the point x equals x equals a, or q equals p, that gives us straight out 0, so that's gone. In fact, the only term that's left upon applying the directional derivative v is this last one here. And so after all of this, we obtain 0 plus 0 plus the sum as mu equals 1 to n, h mu composed with psi evaluated at p, times by v of the muth coordinate of psi. And how can you, why is it that I've only got the second term there? Well, the first one is 0, right? That's just, sorry, the second term is 0. This term here is 0 because it's just a constant, it's just a number, and v of any constant is 0. And now we exploit, remember that h mu at a is df dx mu evaluated at x equals a, and substituting that information in here tells us that v applied to f is really the sum as mu goes from 1 to n of d, we've got to substitute for big F now, which is little f composed with psi inverse, dx mu evaluated at x equals a, or otherwise known as psi p. And then we've got some numbers that we'll call v mu. So these blue thingies here, they are just some numbers which we'll call v mu. And this pinky stuff here is what we get over there. But then look at this expression here. We already named these things x mu of f. So this tells us that v of f is none other than a linear combination of these x mu f's. And we're done. So we've managed to show that any directional derivative operator, any v satisfying conditions 1 and 2 of the Leibniz property in linearity, when applied to a completely arbitrary scalar function on a manifold M, is really just a linear combination of these n coordinate coordinate vectors x mu, and the converse is obvious. So what we have shown is we've not only shown that dimension of this vector space Vp is the hoped for n, we've also presented a basis, and this basis really is the one that carries or connects with the notion of v as a directional derivative on Euclidean space. So it generalizes in a nice way and a natural way. So I gave this basis a name. I said it aloud, but let me just write it down. So this basis x mu of Vp is called the coordinate basis. And it's often denoted, depending on what textbook you look at, x mu could be denoted d dx mu evaluated at p. You might see it as d mu at p, or some people just omit the p. You never know, right? E mu, oops. The textbook you pick up will denote this basis in different notation depending. So be prepared for there to be a wide variety of notations here for this basis. Now I'd just like to draw a little picture. Here's my cartoon of M again, of this basis. What does it look like? Or what are you meant to think? So here's M, here's d dx mu at p, and you really are meant to think of it as a vector tangent to M. Of course, you can't say the words tangent to M without thinking of there being an ambient space, but you think of at each point P there's one of these d dx mu thingies, and under psi, under this coordinate chart psi, this vector operator at P becomes literally the vector operator that goes in the coordinate direction, the corresponding coordinate direction in Rn. So at psi P, this operator becomes d dx mu at psi P. And so all these, this is a field of operators, and under psi, or in the corresponding coordinate chart, all these vectors point exactly along the coordinate direction mu. Okay, so that's how you're meant to think of these. They're operators, they eat scalar functions on the manifold, and they correspond to at a point with the notion of a directional derivative in Euclidean space at that point. Okay, suppose, but is it well defined? Is this notion now a good notion, or have we just done something silly and introduced something horribly coordinate dependent? Well, let's find out. Suppose we had chosen a different coordinate system. or a different chart. Then we would have done everything with respect to a new or different coordinate basis. So we're going to introduce a second coordinate basis, which we'll have to call x prime new. But can we express our first coordinate basis in terms of our second coordinate basis? Well, you betcha, right? So x mu, our original coordinate basis, is a linear combination of these new coordinate bases. And what kind of linear combination is it? Well, you've got to compute the Jacobian, or the derivative of the nth coordinate in the new basis with respect to the muth coordinate in the old basis at psi of p. That's the linear combination. So this is a little exercise for you just to prove that there. So that allows you to express one tangent vector expressed in one coordinate basis with respect to a new coordinate basis. So little x prime new denotes the nth component of psi prime composed psi inverse. Now I realize that we've got big X's and little x's in this story, and the notation may not be entirely clear. So let me just go backwards here through the notes and just slightly use a notation that update the notation here slightly to clarify this. So we have this x mu here. This is meant to be a capital X, and this is meant to be this thing in blue is meant to be a little x. So the thing in yellow, that's a capital X. And the thing in blue is lowercase. So this potential confusion won't last for so long. Basically assume every x is lowercase unless I put little serifs on it. So I'm just looking through here the notes to see if I've used any other instances of capital X. Here's one other instance of capital X here. Here's a capital X here. Capital X here. Capital X here. Here's another capital. Here's a capital. And those are little x's. So assume that all x's are lowercase unless I take some time to decorate them with serifs. In the end, these kind of things shouldn't cause too much confusion, because often the object that you're talking about is clear from the context, and by context I mean the things that it acts on. Okay, so now we know how to express one coordinate basis in terms of, for one chart, in terms of the coordinates of another chart. Now we're about ready to start building up mechanics on smooth manifolds. So we've presented a nice basis, x mu, for our tangent space Vp. That means that any tangent vector is a linear combination of this basis, or whatever basis takes your fancy, with respect to whatever coordinate chart takes your fancy. So always now, we can express tangent vectors in terms of this basis. And if you had chosen to use a different coordinate chart, or you're forced by circumstance to express your results in terms of another coordinate chart, then you can express your tangent vectors in the new basis using this transformation rule that I wrote before. So these coefficients of our vector v, our tangent vector v, in a new basis, you can find them by multiplying them by this Jacobian factor. And this thing here has a name. This is the vector transformation law. And so now we've got a way to express vectors in one basis with respect to another basis. We have a coordinate, effectively we have the building blocks for a coordinate-free notion of a tangent vector. And now we can do mechanics, do a little bit of mechanics. So to do mechanics, you need to have the notion of a trajectory, of a test particle. So a trajectory is none other than a smooth curve so we have a test particle moving in a manifold M, and we need a notion of a smooth curve that it follows. It doesn't have to be smooth, but we're going to stick with smooth throughout this course, is a C infinity map C, which goes from R into M, or an interval thereof. C could go from an interval I into M. You don't have to have an infinitely long trajectory. You could have sort of trajectory segments. They're also smooth curves. So the picture you should have here is that you have the real numbers here. You think of that as time, proper time. And C is a map that takes the flat Euclidean one-dimensional space R and gives us an image for each point. So C is this map, and then when applied to R, it gives us this lovely trajectory inside M, like so. It's the image of C. And at one point on R, C gives us the point P itself. Now here's a nice thing. If you have a curve, a smooth curve in M, you can associate to each point P on C a tangent vector. So how do you go from having a curve to a tangent vector? Well, this is the way some textbooks present tangent vectors in the first case. So what you do is you set for a given f, a given smooth function on M, what you do is you set the t of f, this is to be our differential directional derivative. How do you get it? Well, what you should do is you differentiate along the curve the function composed with C, and then evaluate it at the point P. And then it's just a chain rule away from expressing things in our old notation. big X mu of F. Oops. Where I've introduced some notation here. The muth component of psi composed with C is just called X mu of T. Okay, so that's how we get from a curve in a manifold, we can get a directional derivative operator. Now, it's worth saying that this expansion works for any coordinate basis, right? Any coordinate basis. And we always find that the components of our tangent vector are given by d mu, dx mu dt, like so. So I've said it already many times, but I may as well write it out now. Again, Vp, this vector space of directional derivatives obeying linearity in Leibniz, is called the tangent space at P. So this is just the tangent space at a given point. We can tangent space, we can also define tangent space for the whole manifold. What is that? Well, we just take the union, we stick together all the tangent spaces for every point P on the manifold. So if you take U of P of V of P, we might give that a name, we might call it Tm. So stick all these vector spaces together. Now what do you have? You have the full tangent space for M. Now comes the warning. You know, we've tried to build a vector space. You know, although our manifolds, we can no longer, our smooth manifolds may not necessarily be vector spaces. We've managed to associate a vector space to each point of a smooth manifold. And you might start wondering, well, you know, looks a bit like M is a vector space. Okay, this is where you've got to be real careful. So although the dimensions of these vector spaces at all these different points are the same, right? That was the theorem we proved. For all points in M, the dimensions of these vector spaces are the same. Although that is true, and further, right, when two vector spaces have the same dimension, they're isomorphic. There exists an isomorphism between them. So thus Vp is the same as Vq. There exists an orthogonal linear, or there exists a linear transformation which identifies Vp with Vq. Invertible linear transformation. These are isomorphic vector spaces for all P and Q. Although there exist these isomorphisms, they're not natural. They're chosen, there's no canonical way to choose an isomorphism between two vector spaces without extra data. There's no standard way to choose this isomorphism. Isomorphism means identification. In particular, you could have 2 points that are really close, and the isomorphisms or this identifications between these two vector spaces is wildly varying, like super wildly varying as you change the points around the manifold. You might think that's absurd. I'm sure I could choose a smooth way of doing it. Well, yeah. You can, but you need a little bit of extra data. So this isomorphism could be quite wild. To get a good choice, and I won't tell you what good means yet, just put it in quote marks, get a good choice, you need a bit of extra data. Okay, so we can think of these tangent spaces as being there, canonically associated to each point of the manifold. We can almost think of them as being like the same, and as soon as you can identify one tangent vector with another, then you'll be able to add and subtract tangent vectors at different places. But we can't do it yet. We actually need a bit more information. And that's the extra data that you get from a metric, which we'll introduce in some later lectures, but not now. For now, we're going to talk about manifolds without metric, without this extra data. Okay, we're almost at sort of doing a bit of mechanics on manifolds. So a tangent field, so we've talked about tangent vectors. Now we can talk about a thing called a field now. What is a tangent field? Well, it's just an assignment of tangent vectors, right? You know, one for each point. I even drew a couple. So it's an assignment of a tangent vector, one for each point of the manifold. That's what a tangent field is, dot. We can characterize tangent vectors, tangent fields. So we can, you know, some tangent fields are better than others. So we say V is smooth if for all f, for all smooth functions on our manifold M, when you apply V to f at P, well, sorry, V applied to f is a C infinity function. So it's really interesting that smoothness of a vector field can be defined without this extra data of a metric. Even though we're formally not allowed, because we can define this notion without requiring without requiring that we compare vectors at nearby points. It's kind of interesting that we get away with it. Okay, there's a little lemma we should say. So the coordinate basis fields, now we can define a coordinate basis field, capital X of mu, they're all smooth in the sense above. And the proof is, this will give you some insights perhaps even into the definition of smoothness. What you do is you apply this x mu to your favorite smooth function. Here's how you apply it to an arbitrary function on the manifold. And if you allow P to be the argument, you can see that because psi is smooth, f is smooth, the first derivative is smooth, and then you evaluate it for an arbitrary p, you get a smooth function of p. Cool. And thus, an arbitrary tangent vector is a linear combination of x mu, sorry, not thus, since an arbitrary tangent vector is a linear combination of the x mu's, we proved that in the theorem. An arbitrary tangent vector v is a linear combination of these x mu's, then v is smooth if and only if its components v mu are smooth. It's gives us a nice criterion to determine if we have a smooth vector field. So we've pretty much built everything up now to talk about a rudimentary form of mechanics on manifolds, right? So we've got the notion of a tangent vector field, and we've got the notion of a smooth curve. So with it, we can define a velocity field, right? A velocity field is just a tangent vector field. And the solution to the equations of motion is a smooth curve C with t, the tangent vector to the curve, literally being v of f. Right? Okay, that's a topic we'll get into in the next lecture, but for today we are finished. So thank you very much for your time, and I look forward to seeing you next week. Goodbye.